In our first example, we want to find the volume by the shell method, formed when we rotate the area bounded by this region, these two vertical lines, and the x-axis about the y-axis. So first things first, if we're using the shell method, that formula is that volume is equal to 2 pi, the integral from a to b, p of x times h of x dx, or it could happen in terms of y, p of y times h of y dy. And I'll just change these to C and D. So first I'm going to draw a sketch of what this region looks like for us to figure out if we're integrating with respect to x or if we're integrating with respect to y. So I have a graph here of the function. I'm going to zoom in because I'm really only interested in what's happening when x is 0, which is right there, and when x is 1, which is where that hits the x-axis. So the region that I'm working with is that little region right there, where this is the point 1, 0, and that's at the origin. And we're going to be rotating about the y-axis. So when we rotate this about the y-axis, we'll see a reflected region pop up on the negative side, and it will form a 3D shape. Now that we have our region drawn, let's go in and focus on what our representative rectangle will look like. In the shell method, we always want to make sure that the representative rectangle is parallel to the axis of revolution. So if we're rotating around the y-axis, I will draw our representative rectangle here. The two things that we need to calculate are p of x, the distance from the rectangle to the axis of revolution, and we also need to calculate h of x, the height of the rectangle. So let's start with finding the distance from the rectangle to the axis of revolution. Let's start with finding our p of x, this distance here. Well, what is that distance? We know that it's less than 1 because we know that this goes over to 1, but to be honest, we don't know exactly what that distance is, because hypothetically, I could have put the representative rectangle there, and then the distance would have just been this much. Still just some arbitrary distance x. I just choose an x value between 0 and 1, and I move over that much. So p of x is simply just x. Now, depending on which x value I choose will determine the height of the rectangle. How does it determine the height of the rectangle? Well, whichever x value I choose, I take that x value and I plug it into this function. That determines how tall that rectangle is. The height of the rectangle is just the function. So now we have our p of x and our h of x to use the shell formula. We still need our a and our b. We are integrating with respect to x because our rectangle hits the x-axis, and our x values run from 0 to 1 over the region that we're integrating. So our volume integral looks like 2 pi, the integral from 0 to 1 of p of x, which is x, times h of x, which is x minus x cubed. Again, I'll point out at this point, kind of very similar to what we saw in the last lesson, we are no longer working with Calc 2. This is now an integral from Calculus 1. We just need to distribute, simplify on the inside, integrate, apply the fundamental theorem of calculus to get a final answer of 4 pi over 15. We're going to look at another example using the shell method. We have several graphs here. The first equation is the red graph, and then we have the y-axis, vertical line x is equal to 0. We have the x-axis, horizontal line bounding us at the bottom, and then we also have the horizontal line y is equal to 1. So there is our region that we are rotating. So when we rotate that region, we'll see a shape formed down here. When we spin that region, we'll see a shape formed down here because we are rotating around the x-axis. Rotating around the x-axis, and we want to use the shell method. So we want our representative rectangle to be parallel to the axis of revolution. So here is our representative rectangle. Notice that that rectangle hits the y-axis. It does not hit the x-axis. So everything in this integral is going to be happening in terms of y. Formula for the shell method, 2 pi. I'm using c and d just because I'm using y here. And everything in the integral will be written in terms of y. So let's figure out what p of y is. P of y is the distance from the representative rectangle to the axis of revolution. So what is that vertical distance there? Well, I know it's between 0 and 1, but I don't know exactly what it is, and it could change because I could have put the rectangle up there. But whatever I do choose to choose the rectangle, I'm essentially choosing some y value between 0 and 1. So our p of y is just y. H of y is how long this rectangle is. What is the width of that rectangle, or the length of that rectangle? Well, the length of that rectangle is whatever x coordinate this point hits the graph at. Hits the graph at some xy, but xy is how long, but x is how long that rectangle is. Well, we need to write x in terms of y. Remember, we want everything in this integral to be written in terms of y. So this equation tells us what x is equal to in terms of y. So h of y is e to the negative y squared. Integrating with respect to y. Think about our limits on our integral. Everything needs to be in terms of y. We go from 0 to 1, and we'll keep the 2 pi in front. So now we need to evaluate this integral. This integral can be evaluated using u substitution. I noticed that because I see in the exponent here, I have a negative y squared, which means that du is negative 2y dy. I don't have that negative 2. I can manipulate my coefficients. So the integral would be substituted. Notice I'm not putting limits on this integral right now. I'm going to replace the y dy with the negative 1/2 du. So I'll just stick the du at the end, and I'll stick the negative 1/2 out in front. And then I'm replacing the e to the negative y squared with an e to the u. And then as for my limits, well, we had we had y limits of 0 and 1, and we used the substitution that u was negative y squared. So the new limits change to 0 and negative 1. Do make sure that you keep the same order that you had originally. So if 1 was the upper limit, I plugged in 1, I got out negative 1. Negative 1 should be the new upper limit. I'll finish simplifying this. The integral of e to the u is e to the u, and we will evaluate that from 0 to negative 1. Starting with negative 1, e to the negative 1 minus e to the 0. E to the negative 1 is 1 over e. E to the 0 is... In this example, we will use the shell method to find the volume of the region bounded by the graphs of the parabola y is equal to x squared plus 1, the x-axis, the y-axis, and the vertical line x is equal to 1. So here's a graph of the parabola. Y is equal to x squared plus 1. Make sure and label both my axes. We have the horizontal line, y is equal to 0. That's just the x-axis. And we also have the vertical line, x is equal to 0. That's just the y-axis. And we have the vertical line, x is equal to 1. So this is what the region looks like. We're rotating about the y-axis, so we'll form another region on this side to give us our 3D shape. We want to use the shell method, so our representative rectangle needs to be parallel to the axis of revolution. Notice that the rectangle hits the x-axis, and so we need everything to be in terms of x in this integral. So we have p of x, which is the distance from the axis of revolution to that representative rectangle. That is simply x. It's just some horizontal distance x that we decided to move over. And the height of this rectangle, how tall that rectangle is, well, that is the y value that we get when we plug x into our function. It is just x squared plus 1, which is the function value there. So now using the shell method, we have our formula that volume is 2 pi, the integral from a to b, p of x times h of x dx. Let's talk about our limits of integration. Everything in this integral is in terms of x, as our rectangle hits the x-axis. Our region starts at an x value of 0 and ends at an x value of 1. And we'll take p of x and multiply it by h of x. And at this point, we now have an integral from calculus 1 that we can easily integrate by distributing the x and applying the power rule. Followed by the fundamental theorem of calculus to get a final answer of 3 pi over 2. So to get started, I graphed the function and the horizontal line y is equal to 1 in my calculator. So I have a cubic function that goes through the point 0, 1 and the horizontal line of y is equal to 1. So first I'm just going to get a sketch of what that looks like. We have a cubic function that goes through 0, 1, like that. We have a horizontal line of y is equal to 1. And we have the vertical line x is equal to 1. So this is the region that we're working with right there. And we're rotating about the line x is equal to 2. So the line x equal to 2 is somewhere over here. And we're going to rotate about that line. So we actually form a solid where the reflection of it is somewhere over here after that spins around that region. Okay. What's important though is that we're using the shell method. This is the shell method section, so I'm going to use the shell method here. I will mention that I could use the washer method. I could think of a capital R and a little r. Think back to the previous lesson, but let's look at the shell method where instead of putting rectangles perpendicular to the axis of revolution, I put my rectangles parallel to the axis of revolution. And I have to think, what is the distance from that rectangle to this axis of revolution? Notice that the rectangle does extend vertically, so it would hit the x-axis. Everything will be in terms of x. P of x, that distance I'm going to find by right minus left. The right side of this distance starts at 2, and the left side is at whatever x value we chose to put the rectangle. So P of x is 2 minus x. Let's talk about h of x, which is the height of that rectangle. We're going to find by top minus bottom. Top of that rectangle hits the cubic function. The bottom of that rectangle hits the horizontal line, y is equal to 1. So we have P of x and we have h of x. I went ahead and simplified h of x by canceling these 1's, and here's our formula for volume by shell method. We're integrating with respect to x. The x limits run over the region that we have from 0 to 1. P of x is 2 minus x. H of x is x cubed plus x. We will take this product. And again, I will mention that at this point, we are simply working with a definite integral from calculus 1, where we're just going to simplify this on the inside and integrate this as normal. So first we multiply it out, apply the power rule, and now I'm going to apply the fundamental theorem of calculus to get a final answer of 29 pi over 15.